Okay, hi there. Welcome to the video on single replacement reactions. The first thing I want to talk about is I just want to establish how I would like to represent different kinds of substances going forward. All right, so, and this is going to be something we'll use a lot, I think, in the coming months, starting with this single replacement reaction stuff. So the first thing, we've got metallic substances, ionic compounds, and aqueous solutions. And so here's the way I'd like to do this. I'd like to represent metallic compounds using this sort of a visual representation because in a pure metal like pure copper, pure iron, the atoms are arranged in this lattice structure. So it's similar to ionic, but instead of having cations and anions, you just have, you've got the metal atoms arranged side by side, up and down, in this array pattern. Okay, ionic compounds we can think of as alternating cations, anions. Okay, so you always have cation, cation, and so on, so that every ion is surrounded by oppositely charged ions, and that leads to great stability. And then aqueous. Okay, so for example, we're working with copper 2 chloride. So copper 2 chloride in the aqueous phase could be represented as copper cations separate from chloride anions, and in water solution the cations, the metal cations, are going to be surrounded by water molecules, and the water molecules are going to have a very definite orientation. They're going to point their negatively charged oxygen atoms at the cation. For the chloride ions, it's just the reverse. The waters are now going to congregate around the negative charge and point their positively charged hydrogen atoms. Okay, so these are three representations that I'd like us to use, and so if you see this in the future, you'll kind of know what I mean. Okay, now specifically, let's try to go a little deeper and see if we can explain what we observed in lab when we did when we took the iron nail and reacted it with copper 2 chloride solution. Okay, so here's the beginning of the reaction. Here I'm representing the metal with this array of iron atoms. So you can think of this as like a, just a very tiny little section of the nail that we used in the lab. Okay, so here comes the copper 2 plus ion, and you may be saying, hey, where's the chloride ions? Well, they're out there. They're there too, but the real the business end of this chemical reaction is between the iron and the copper. All right, and since this is a single replacement, you know that the iron is going to be replacing the copper in the copper chloride solution. And so let's focus on what the copper is doing. Okay, so here comes copper. It's getting ready to come into contact with the iron nail. It's surrounded by the water molecules. Well, to really get in there and make contact, it's got to shed that one water molecule. And so now we have the neutral iron atom in contact with the copper 2 cation. And now this is where this is where stuff happens. This is where the chemistry happens. All right, so let's focus on these two guys. And I think before we actually talk about the atoms, I think to understand what's going on with the electrons, there's going to be an electron exchange here. And to kind of get a feel for what's going on, I think it's good to look at Mr. Iron and Miss Copper and think about the electrons, make an analogy between electrons and like a winter coat. All right, so it's a cold winter day. Here's Mr. Iron. He's very happy. He has this warm winter coat, and that kind of represents the electrons. Now over here's Miss Copper, and she's like, she doesn't have a nice coat, so she's really cold and she's unhappy. So there's this, kind of this tug of war that ensues between the two the two people, and you know, maybe Miss Copper's going to win. So she's going to grab that coat from Mr. Iron, and then he's not so happy anymore. Now she's happy. And if this was the case, if this is what happened, in chemistry, we would say that iron is more reactive than copper. And it's more reactive in the sense that iron is more willing to give up the electrons. Okay? So just in general, I want you to keep in the back of your mind that what makes an element reactive is its propensity to give up its electrons. All right? But conversely, you know, the other side of the coin here is that copper is showing a stronger attraction for the electrons than iron. All right? So if this is what's going to happen, if Miss Copper is going to win the battle of the coat or the electrons, then we could make these two statements. Now, but who knows? Maybe Mr. Iron is going to win the tug of war of the electrons. And if that was the case, all right, so this is like the opposite situation. If Mr. Iron is going to win, then we would say that copper is more reactive than iron, okay, because copper was more willing to give up the electrons, and therefore iron must have a stronger attraction for the electrons. Okay, so, and you know, it can't be both. It's going to be one or the other, and we'll find out. Now let's go back. Let's really zoom in on the actual atoms. So here's a neutral atom of iron, and I'm representing the outer shell with 3 electrons. All right, because iron can become it can become 3 plus, and that means it has, you know, 3 electrons that it can give up. Meanwhile, here's copper 2 plus, and you can tell by the dashed lines that, you know, here's where it can hold 2 electrons if it wants to become neutral. All right, but right now it's 2 plus because it's you know, short 2 electrons. Now, if copper has a stronger pull on electrons than iron, then this is what's going to happen, right? So 2 electrons are going to get yanked off of iron, and they're going to get transferred over to copper. And in the process, iron will become 2 plus, right, because it's deficient 2 electrons, and copper will go from 2 plus to neutral, so there's no charge in here. Okay, so that's one scenario. Now, what if it goes the other way? What if, in fact, iron has the stronger attraction for the electrons? Well, then we would be back to where we started, right? We'd have neutral iron, copper 2 plus. Well, which way is it? Well, on page 333 of your textbook, this is for level 2, you'll find this activity series, and this is a little bit more extensive, a more extensive list than you'll find even on page 233. But anyway, what you can see is that there is an order to the reactivity of elements. So lithium is one of the most reactive elements. It's very willing to give up its electrons, followed by potassium, and then sodium, magnesium, and so on. At the other end of the spectrum, here we have gold and platinum and silver, and these guys are very reluctant to give up electrons. They're not very reactive. Now, let's specifically look at our two players here, iron and copper. Where are they in the ranking, and what's their relative position? Well, you can see that iron here is higher up on the list, which means it is more reactive, which means that it is more, you know, willing to give up its electrons than copper, and so therefore copper is going to win the battle of the electrons here. Okay, so let's recap. So here we've started writing the reaction. We got iron, metallic iron, that was in the nail. You've got copper 2 chloride, that was in the solution. And in fact, by looking at our activity list, we can tell that iron is more reactive. It's going to give the electrons. That's going to allow copper to become solid copper, and then iron will go into solution to become, you know, iron 2 chloride. what does this look like now? If we think about the nail, and I think you remember the nail turned kind of a rust color. Well, that was actually copper, metallic copper that was plating onto the iron nail. So here's what happens. All right. So again, here comes copper with its entourage of waters. The two get together. We now know that copper is going to win this battle for electrons. So 2 electrons will transfer from iron to copper, and in the process they'll switch places, and copper, now that it's neutral, it will plate on the surface of the the iron nail. The iron, having become ionized, it goes into the water. It no longer wants to be hanging out with the other neutral irons. It's going to be more attracted to the water, and then it goes off into solution to become iron 2 chloride. And here now, this is the last last slide, just wrapping up. I've added the states of matter labels, and so I think hopefully now you can see from beginning to end, what's going on both at the atomic scale and what's going on in our representation of the chemical equation, and how it all kind of hangs together. Okay, thank you very much for listening.